Detecting Edgeworth Cycles with Timothy Holt and Simon Scheidegger. I have been working on empirical dynamic games in I/O, that is, models of strategic industry dynamics and their empirical implementation about innovation, mergers, and collusion. In my previous work, I proposed a dynamic structural analysis of collusion and studied the case of a hardcore cartel in the vitamin markets. That paper took a long time to publish, but now it's done. And since then, I've been wondering about what to do next. One thing I wanted to do is to analyze less explicit forms of collusion than a cartel agreement, such as price leadership dynamics. For example, an industry leader raises its price and everyone else follows. At some point, firms undercut each other, so prices come down. And then when prices get too low, someone dares to raise prices again and everyone follows. Actually, it's not even clear if we should call such pricing dynamics a collusion, because we don't really need a collusive equilibrium to rationalize such patterns. Maskin and Tirol 88 show that a Markov perfect equilibrium, MPE, of a simple dynamic oligopoly model can generate Edgeworth cycles without any repeated games type strategies. That is, I change my price today to maximize my expected value based on your choice of price yesterday. And then you change your price tomorrow to maximize your expected value based on my choice of price today. And then I'll change my price again the day after, and so on, without any collusive agreement between us. So that's Markov perfect equilibria. And they showed that there are Markov perfect equilibria that look like Edgeworth cycles, like in this picture. This another example is an empirical one from Byrne and Roos 2019. Their study of the retail gasoline prices in Western Australia. This is the clearest example to date. So there are such things as Edgeworth cycles in reality. Who cares about such cycles? Why do we care? It turns out many people do, because the patterns are so funny and they look artificial and conspiratorial. Why do gas stations increase prices so fast and decrease prices so slowly? They must be doing something funny, something to increase profits. That's how they think about it. And the way they do, it looks kind of like suspicious. That's how consumers, politicians, and government agencies have reacted to such patterns. And there are real cases of price fixing collusion, some of them totally illegal. One example comes from Clark and Wood's study of a cartel case in Canada. Another example is from Norway, where there's an industry-wide scheme to follow some weekly cyclical patterns. And then Wang, 2008, studied an Australian cartel case. So yes, for good reasons, people suspect something anti-competitive, something anti-consumer might be going on. Here, an obvious empirical sanity check would be to get data, classify observations into cycling ones and non-cycling ones, and then see how prices and markups are correlated with cycles. And many people did study their statistical relationships. The first 3 studies found positive correlations in America, Canada, and Australia. But the following 3 found negative correlations in America, again, America, and Canada. So the evidence is definitely mixed, perhaps naturally so, because, well, one reason could be that there are just so many different countries and regions, and it's kind of obvious there's some heterogeneity across countries and regions. But there's another obvious issue that received relatively little attention in the literature. That is, defining and detecting Edgeworth cycles is not as simple as you might imagine. Some papers just eyeball the data to say there are cyclical patterns, while others use some operational definitions that are kind of ad hoc. In fact, I haven't seen a paper that defined Edgeworth cycles in any formal or scalable manner. So we might need a good detection method or two or three. Why? For one thing, we want to be able to scale detection approach because we can't eyeball all big data sets that are becoming increasingly available. Two, reliability might be limited if you just choose ad hoc definition for each data set. It's a little hard to generalize, and one method might be detecting something totally irrelevant in another data set. And three, replicability. If we can come up with a systematic approach, then there's a hope that the approach can be repeated and applied elsewhere to, well, possibly many other regions and countries, and possibly outside retail gasoline markets. Because the reason people studied retail gasoline prices so much is that typically relatively high frequency price information is available. But then once such data become available in other markets and industries, we can hope to use the approach developed in this market to detect similar patterns elsewhere. Even if you are not an IO economist, or you don't care about Edgeworth cycles per se, there is some lessons from this paper, because this paper, well, hopefully demonstrates how we economists can exploit recent advances in machine learning to solve pattern recognition problems. Not just any pattern recognitions, but patterns that actually matter in economics and for public policy. So that's where this paper is going. First, I'll show 4 existing methods from the literature, or how we standardize and formalize such methods as estimable models. Then I'll explain 6 new methods that we propose. 3, we'll show data and explain our manual classification approach to set a ground truth in terms of whether cycles exist or not. And finally, we show the results of a horse race between 10 methods, plus some substantive findings about markups and cycles. Here are my 2 co-authors. Simon Scheidegger at Lausanne gave tons of scientific advice as to what kind of new approaches would be suitable. And then all the computational implementation was done by Tim Holt at currently in Lugano. So let me first introduce 4 existing methods. Because there are so many methods that I'll end up introducing, I color-coded 10 from dark colors to bright colors, like in the rainbow spectrum. The first one is what we call positive runs versus negative runs. Think of upward price increase as a phase, or positive runs of price changes, and negative price changes as, well, negative runs. We can measure the duration of each phase and calculate the average duration. If the mean duration of positive runs is shorter than the mean length of negative runs, that suggests the price increase phase is short and rapid, whereas price decrease phase is kind of gradual and slow. And that's one asymmetry that's present in Edgeworth cycles. So this method focuses on asymmetry. We can allow a constant or scalar term with theta as an adjustable parameter that defines the exact threshold above which or below which we say this is Edgeworth. Similarly, method 2 focuses on asymmetry, this time comparing the magnitude of mean increase versus mean decrease. If the mean decrease is larger than mean decrease, that is, again, indicative of asymmetric patterns where price increases are sudden and big, whereas price decreases are, well, smaller and gradual. Third, another maybe even simpler way to capture the notion of asymmetry of Edgeworth type is to just calculate the median price change, median daily price change. If that is negative or significantly negative, below 0, say adjusted by this threshold parameter theta, then that might be indicative of many price decreases relative to, well, fewer instances of price increases. That's a smart way to capture asymmetry. And the final and fourth method is what we call many big price increases, used mostly by Byrne and Roos 2019 in Western Australia. This is the only method among the existing 4 that uses 2 parameters. One, theta 1, determines the threshold above which a price increase is considered big enough, which is one characteristic of Edgeworth cycles. And then the second parameter, theta 2, is the threshold for how many such big price increases must occur within a calendar quarter or a year, so that the data pattern qualifies as Edgeworth cycles. Please note that while methods 1, 2, and 3 focused exclusively on asymmetry, this method 4 captures both the amplitude aspect, how big the price change is, and the frequency aspect of cycles. And in that sense, it's a little more sophisticated or complicated and looks at multiple aspects of cyclical patterns. To recap, essentially, the 4 existing methods can be operationalized or formalized as simple threshold models with 1 or 2 parameters. All focus on some notion of asymmetry, but except for the 4th method, not so much on cyclicality. Here comes 6 new methods. Method 5, Fourier transform, which is a mathematical method since the 19th century to detect and characterize periodicity in time series data. We can think of a continuous function of time, say like daily price series for gas stations. We can convert this time series data into what's called frequency domain expression, or power spectrum, or periodogram, this P function. This converts time series patterns, potentially of cyclical patterns, into a set of powers at which each frequency is manifesting. So if some, say, sine wave of certain frequency is predominantly visible in the time series data, then the power spectrum expression or periodogram would suggest high power for that frequency and relatively low numbers for other frequency. So that's one way to transform the time series data into something convenient and reflective of cyclical components. We can use a thresholding idea from the previous methods to set this parameter theta above which if the highest level of power in periodogram surpasses the threshold theta, we might say, okay, significantly cyclical component of frequency f or f max, f star is present in this data. As such, this approach is suitable for regular cycles with maybe deterministic frequency. A more nuanced version of Fourier transform is what's called the Lomskargel periodogram, which is very similar to the spectral analysis method in Fourier transform, but it has some adjustments that would make this method more robust to irregular data patterns, even though our data that we're going to use eventually are not that irregular. One nice thing about this Lomskargel periodogram is that we can interpret its power spectrum as a reflection of something like running an OLS regression of time series data on sine waves of different frequencies. We can think of power spectrum in Lomskargel periodogram as a reflection of such series of regressions. But eventual approach would be similar. Set some threshold parameter value, a scalar, and if the highest point in the periodogram is above the threshold, we would say, okay, significantly strong or strong component of cyclicality at that frequency is visible in the data. So like Fourier transform, this approach is also good for regular deterministic cycles. But then not all data patterns in reality might be that regular or deterministic. So method 7 tries to capture cyclicality in a more flexible, maybe less rigid manner. We fit cubic splines, which is polynomial or cubic continuous function with the third degree polynomial to smooth the discrete daily observations. This is mostly for computational convenience. We can do without cubic splines, even though that might be just one more step computationally burdensome. Anyway, fit cubic splines to make it smooth, and then subtract the mean of the daily price levels. That way, the smooth wavy function would be going above and below 0. Counts the number of times this function crosses 0, or counts the number of real roots in this fitted cubic splines. And that would tell us some notion of frequency in less rigid manner. So our hope is that this approach would be good for irregular and maybe more stochastic frequency cycles than methods 5 and 6. Okay, pushing this idea of flexibility and maybe non-parametric regressions even further, the most complicated or most flexible non-parametric method of today is this method number 8, long short-term memory, or LSTM, which is a specific architecture of recurrent neural networks type of models. And then R and N are by themselves a specific class of neural networks models or deep neural networks models for time series data. And in recent years, it became the de facto industry standard for recognizing, modeling, and predicting speech, handwriting, language, and polyphonic music, and so on. So it's good for capturing kind of realistic noisy patterns that are still meaningful from data, time series type of data. Econometrically, we can think of this as a class of flexible non-parametric models for time series data. Getting into the details a little bit, LSTM is a recursive dynamic model whose behavior centers on pairs of two state variables that are S and C. Here, subscript D denotes our timestamp, day 1, day 2, up to day 90 for each calendar quarter for each gas station, okay? So the raw data are 90 daily observations of data for particular station for particular calendar quarter. Now, this LSTM model processes daily price in this recursive manner. First state variable S is a complicated nonlinear function of another state variable C and the first state variable's past value from either previous day or in previous layer step. There are multiple layers. So for each day, there are 3 layers in our specifications. That means each new daily data would go through this multi-layer screen with potentially many laws of motion that hope to capture subtle different aspects of wavy patterns or cyclical patterns and so on. The second variable, the second state variable C, is what people call cell state to distinguish it from the first main state. The only reason for this second state variable is that while the first state variable is meant to reflect the current short-term state of the whole dynamical system, the second variable, the second state variable, is trying to capture long-term dependence between, say, price level or change in day 7 and day 1 or day 2, or even longer lags, so that we don't miss out bigger picture in time series. And because we prepare many such pairs of two-state variables, 16 of them in one layer, 8 of them in another layer, and 4 of them in the third layer for each day, this model would process 90 daily prices in a serial manner in many steps. There would be about 2,000 effective parameters that are governing the flexible patterns to be captured here. What's surprising is that even though the number of parameters is well, in theory, high, it would work well even with a few hundred observations, as I'll talk about the data requirement later. As such, this is the most flexible of all standalone methods 1 through 8. Methods number 9 and 10 are now aggregators of the first 7 or first 8. This one, method number 9, is aggregating the essential information from methods 1 through 7 in what's called random forests functional form. Each method has its own definitional inequality of H threshold model. For example, method 2, which compared mean increases versus mean decreases, had this mean, well, absolute value of mean price increase versus absolute value of mean price decrease. Subtract the right-hand side, which is this one, from the left-hand side, which is this one. Take that difference as the summary statistic for method 2. For each of the first 7 methods, because each of them involves a definitional inequality, we can construct this gap measure as a summary statistic for each method. Collect them across 7 methods to create a 7 vector, and that vector becomes a set of characteristics for station I in calendar quarter T. And the idea is, even though each method had just simple kind of a monotonic thresholding rule, well, in general, we can come up with multiple thresholds that could be capturing nonlinear patterns or non-monotonic patterns, even combinations and interactions across multiple measures, across methods 1 through 7. And that could tell us more information. Or in other words, this ensemble in random forest is a flexible aggregator that gets more information out of methods 1 through 7. Okay, and finally, in a similar manner, we can think of another aggregator, another ensemble in LSTM framework. That is, on top of method 8, the plain basic LSTM that processed 90 days of raw data, we can add methods 1 through 7's summary statistics that characterized in their own ways how people have used these daily prices to indicate, say, cyclicality and asymmetry. As such, this is the most flexible aggregator that gets hopefully more out of all standalone methods 1 through 8. So here's a summary. For existing methods that mostly focused on asymmetry side, Fourier transform and Lomskargel periodogram collectively, we might call them spectral analysis methods that mostly detect regular deterministic cycles, cubic splines that are flexible and captures more maybe nuanced or irregular stochastic cycles, and then long short-term memory that can capture, well, in principle, any weird patterns. And methods number 9 and 10 that are aggregators of methods 1 through 7 or methods 1 through 8. These are the 10 methods whose performances we compare in real data. And each method is optimized with our training data, which I'm going to explain soon, to maximize the accuracy, either in the training set or in a separate disjunct validation set. Okay, so data and manual classification to establish a ground truth. We use 3 data sets from Western Australia, one region of Australia, another Australian region of New South Wales, and then the entirety of Germany for over 5-6 years to 20 years, all converted to a standardized daily price information for each gas station. We bundle them into station quarter batches, and each station quarter observation is then manually classified by our team of arrays to be either cycling, maybe cycling, and non-cycling. And to set a conservative target for prediction by automatic methods, we use either a reconciled unanimous decision by 2 arrays in this case, or unanimous decision by 3 arrays who worked independently on all data sets in these cases. For Western Australia and New South Wales, because the sample size were manageable, we tried to label almost all of them that could be well classified. And then for Germany, because Germany is a big country, we randomly sampled 10% of observations and asked 3 arrays to label all of them independently. You see that 60% and 70% of Australian data sets are flagged as cycling, clearly, respectively. And then about 40% of German data are, well, considered to be cycling. It took many hours of array work. And the current wage for undergraduate research assistant work at Yale is $13.50 per hour. So total labor cost over a few years turned out to be about 12 or 13,000 US dollars. That's the cost of data creation. So here are some examples from Western Australia. This is an example of cycling station quarter. The horizontal axis is day, and the vertical axis is Australian cents. This is an example of non-cycling patterns according to our human classifiers. This is New South Wales, where the duration or the frequency of cycle could be varying a little more. And non-cycling patterns are, well, obviously non-cycling. German patterns are a little more subtle and maybe noisier, but you can still see something like close to weekly cycles here, or, well, apparently non-cycling patterns. So these are the raw data, just some examples. Okay, now we are ready to go look at results. Accuracy horse race between 10 methods. How much data do we need to reach certain level of accuracy? And finally, more substantive findings on markups and in their correlations with cycles. Here's the results for Western Australia. The vertical axis is percent correctly predicted, which we simply call accuracy. And the horizontal axis is showing the fraction of subsamples that were used for training, for optimizing tuning parameters. Most methods perform near or above 90%. As long as sufficient amount of data are provided for training. And then methods 8, 9, and 10, the most flexible and richest ones, perform near or above 99%. While method 7, the cubic spline one, somewhat is lagging behind, even though 85% seems still reasonable or respectable. In New South Wales, the detection is a little more difficult, so most methods perform near or above 80%. Again, methods 8 through 10 perform near or 85 to 90%, being the top performers. Whereas methods 3 and 7, 3 and 7 give degenerate predictions. That is, because a little more than the majority of station quarter observations in New South Wales are cycling, according to our arrays, you can give a degenerate predictions to predict everything is cycling. If you say everything is cycling, more than half the time you are right, but by pure coincidence. That's like throwing everything randomly. That's what we mean by degenerate predictions. So it's a little surprising that one of the most widely used methods, negative median change method, method 3, doesn't work well in the data set where still certainly conspicuous patterns of cycles are present. And cubic splines don't work too well either. Finally, in Germany, because patterns are more subtle or noisy, most methods fail. These 60%, 70%, 65%, these are not very far from degenerate performance. Whereas method 10 achieves 80%. That is kind of nice, followed by methods 8 and 9. Method 7 does okay. So it looks like the cubic spline approach, which captures cyclicality in less formal manner or less straitjacket manner, can be a little more robust to weird patterns, even though it underperformed most other methods in data sets where cyclicalities and asymmetry were clearer. And then among the existing methods, only method 4, this pink one at 65%, gives non-degenerate predictions. Unfortunately, methods 1 through 3 were all degenerate. How much data, manually classified, manual labels do we need to train these systematic methods appropriately? Methods 1 through 7 and 9 perform surprisingly well with only 0.1% of the label sample. In our context, that means 25, 10, or only 36 observations. That's really small data sets. Methods 8 and 10, the most non-parametric and flexible of the methods, need more data, but eventually outperform all the others. And the critical data size is about 1 to 5%. That is, if these methods, the more complicated methods, 8 and 10, are given at least several hundred observations, that would ensure that these flexible methods would reach close to their best performance levels. And the good news, the real good news, is that several hundred observations are about tens of array hours, not hundreds, not thousands. So that means at Yale University rate of compensation of $13.50 per hour, we would need only at the most a few hundred US to label just enough subsample to train these automatic methods to perform well. So in that sense, our proposed methods, at least even the most complicated or sophisticated ones, are effective as well as economical. Now, the final set of results is about markups and their correlations with cycles. The first three rows are the number of observations, the mean price level, and its standard deviation, according to each of the 10 automatic methods, plus our manual benchmark, our ground truth. And then the next three lines are, again, the number of observations, mean and standard deviation of prices at what's determined to be non-cycling station quarters, again, according to 10+1 methods. So it's easy to calculate the difference between means, mean here and mean there, and the gap is positive across all 10+1 methods in Western Australia. And if we do the t-test for the significance in difference in means, that all the p-values are 0.001. That is, the difference is significantly away from zero at 0.1% significance level. So, okay, in Western Australia, everybody says it's the cycles are positively correlated with markups. In New South Wales, the patterns are similar, although one of the methods, well, one that didn't perform too well here, the cubic splines, suggests the mean difference is negative, suggesting that cycling observations tend to carry lower margins. But then all other methods, as well as our ground truth, suggest the mean difference is positive. So again, the markup cyclicality correlation is positive, suggesting some potential antitrust interest for this phenomenon. But then in the final data set in Germany, methods 1 through 6 would suggest, well, 1 is just totally degenerate, so let's ignore. Method 2 through 6 suggest the mean differences are positive, again flagging potential antitrust or anti-competition concern. But in reality, I mean, in our manual classification by our careful RAs, the mean difference is actually negative, suggesting that cycling observations tend to come with lower, not higher markups. And our flexible methods 7, 8, 9, and 10 correctly capture this negative correlation, mostly at reasonable significance levels. And this discrepancy between methods 1 through 6 versus methods 7, 8, 9, 10 are clearly suggesting that the choice of operational definition for Edgeworth cycles, that is not just about operational details or some slight numerical change, but it's something that could determine your eventual empirical findings. And these are the stylized facts that we try to establish to inform a policy discussion, well, at least in an idealized world. So it turned out a seemingly boring definition and detection of cyclicality could carry a directly policy relevant meanings. So let me conclude. We formalize 4 existing methods, propose 6 new ones, and empirically assess all of their performances in Western Australia, New South Wales, and Germany. Methodologically, we have 3 carry-home messages. 1, the difficulty of cycle detection varies wildly across countries and regions. 2, existing methods work well in Western Australia and New South Wales, where asymmetric cycles are relatively clear, but mostly fail in Germany because not all German cycles fit this Edgeworth-style asymmetry. So in anyone's research going forward about Edgeworth cycles, it would be really useful to distinguish between detecting asymmetry and cyclicality. And finally, the third finding on the methodological side is that non-parametric/machine learning methods, especially LSTM ones, achieve the highest accuracy at reasonable labor cost, which are only tens of RA hours or only a few $100s of research expenditure. That's manageable for individual researchers, or I think government agencies. And finally, the substantive conclusion or take-home message from this study is that whether researchers find a positive, negative, or no correlations between gas stations' profit margins and existence of cycles could critically depend on the choice of operational definitions and detection methods. So, because the discovery of facts should inform subsequent policy interventions, these seemingly innocuous methodological considerations are consequential and directly policy relevant. So much so that in our Appendix D, at the end of the paper, we would give kind of a step-by-step recommendations for, well, mostly recipe for practitioners in coming up with economical but reasonably precise ways to capture asymmetric cycles and assess markups correlations. Thank you very much.